All right, so let's see what we had last day. We tried to solve a 2-degree freedom system, right? So this is where we got last day. We dealing with the 2-degree freedom system. We managed to find the stiffness matrix and the mass matrix. We used them and we found the natural frequencies and something else, something extra, which for a 1 degree of freedom, we didn't have that one. And that was something that we call it mode shapes. Mode shape, we define it as what a system naturally would like to do. So for example, this 2-degree of freedom system, we discovered that this system naturally on its own wish to have two, let's say, two shape of motions, if you want to call it. One is that the two masses, they like to move together, back and forth, or here in this case, ups and down, same direction. But with the ratio, which we found that ratio is 0.618. And the second mode shape, these two masses, they like, or they wish to move in the opposite direction, with which frequency? Omega-2, and in the opposite direction. And always they have to maintain this ratio. This ratio, we call them mode shapes, all right? So next step, and I showed you the motion of, like with that demo, the motion of two masses. Now, our next step is that I have initial conditions. I want to solve them. I'm going to write it down again here for a single degree of freedom system. So then quickly we can compare what we are dealing with. So on the left, we have single degree, right? And over here, we have 2 degree. So this is single degree or 1 degree. So in a single degree, you saw we had the equation as mx double dot plus kx equal to 0. And over here now we have m, a vector of x double dot plus a matrix of k, a vector of x equal to 0. All right. So we managed to find natural frequency here, omega n, which was simply k over m. And for this one, we will solve the determinant of k minus omega squared m equal to 0. And we find omega 1 and omega 2, two natural frequencies. All right. So, and an extra information that we found was for this one, we found x1 over x2, a number, right? A constant number. For example, the example that we solved, it was, let me write it down a little bit over here so I have room. Okay. So we found, for the example, this number was 618. 618, right? And then with natural frequency of 2, we found x1, x2, which was minus 1, 618. It is just coincident for this example, this number 618 and 1.618 are similar. They can be any number. They can be positive or negative. Even they can be 0. We will have cases where they are 0, which has their own meaning. But for now, we know these numbers has meaning, right? And we call them this one mode shape 1 and mode shape 2. Right? For each, we have the natural frequencies. One more thing that we do to make our life easier for later calculation. So let's take a look at only x1. So this is x1 and this is x2. x1 over x2 equal to 1. This is a ratio, right? So what I will do, I will choose an arbitrary number for x2 or for x1. So any number. I set x2 equal to 1. 1 is easier. It can be 2, it can be 10, it can be even negative numbers, whatever you wish. It can be 0.5, any number. So, and from here, I will find out x1 is 618. And what I will do, and I need more room, I will show this mode 1 as 618 and 1. This is what we will call mode 1. So just one way to show the mode shapes. Rather than showing it with that ratio, we'll just use this vector form. We'll say, now by looking at this, we will say if my x2 is 1, my x1 is going to be 0.618. As I said, it doesn't have to be 1. Of course, 0 is useless. You can go with 10, but I prefer 1 because 1 is easier to deal with. The same things for the mode 2. I will have mode 2 x2, which will be, if I set this one 1, this one will be 680. Okay, so that's just one way to show the result for a single, for a n degree of freedom system. But for now, just 2 degree of freedom system. So I just learned for next time, I should have more rooms here in this slide, or maybe one extra slides. So far I believe it's clear what just happened, right? We have a 2 degree of freedom system. We found their natural frequency, 2 natural frequency, and we found the ratio. We show the ratio as like in a vector format, and we call them mode 1 and mode 2. Right? So this is mode 1 and this is mode 2. Nothing special. This is simple algebra. So let's go back to the idea of solving the equation. So when we want to solve the equation, we need to have some initial condition. Like in a single degree of freedom, we had x0 and v0, right? And what we did, simply we said, well, my response xt is a constant cosine omega nt plus b sine omega nt. And we managed to find a and b. We have 1 natural frequency, and we say the motion is sine and cosine of that natural frequency. Now I have 2 natural frequency, right? So the result or the response will be a combination of these 2 natural frequency. How they combine? The contribution from the mode shapes, right? So this is, I'm going to write it down so let's show it, and then we will use it in an example, so we'll see how it works. So if I have a 2 degree of freedom system, let's say I have initial condition. My initial condition now, I need them for both x1 and x2, and initial velocities, v1 and v2. We show them in a vector format, right? And I would say the response of this system is very similar to the single degree of freedom system, except this time I have omega 1 and omega 2. So you will see over here, the first portion is coming from omega 1. The second portion is coming from omega 2. And they are very similar to what we had before. So this time I have my constant A, B, C, and D. Remember, we have 2 systems. Previously, we had only A and B. Now we have A, B, C, and D, 4 unknowns, which we need to find them from initial condition. One extra things that we have here is that mode shapes. These mode shapes, they are here. All right. So why they are there? Again, going back to that idea of these 2 degree of freedom system, you saw, we said this system, if I disturb it in a way that x1 over x2, the ratio of these two is just that fixed number. These two goes ups and down together. If I disturb the system in a way that this system, the ratio is -1 over 618, then they are going to have an independent motion, right? One of them, they go ups and down together, another one, the opposite direction. However, if I disturb them randomly, so I don't follow this ratio, then they can have combination of motions. But still, this ratio is going to stay the same. That's part of the natural motion of this system. Okay. So we accept this formula as is, but it will become clear. Let's solve one example, so we'll see how we can use it. Okay. For now, maybe a little bit vague, but wait for it. So this example, I want your attention for the rest of the class. We're just going to focus on this example. We'll solve it step by step. And if you understand this one, we will be done with NDOF, the first part of NDOF. And then the next part will be easy because we are just going to add external force and then damping, of course. We're going to do the same things that we did for SDOF. But this is the main part that you need to understand. So I have a system, 2 degree of freedom system. I have my x1, x2, and I have some initial conditions. So maybe question gives me some extra information. It gives me K, the stiffness. Let's for now set it to just a round number, 100 Newton per meter, and mass of this system, maybe 1 kilogram. But for now, we'll just use parameters. At the very end, we substitute them. So I want to find out the equation of motion for these two masses, how they move if I have this initial condition. Step number 1, I'll draw the free body diagrams, or I use a Lagrange equations. So step number 1 is find the differential equations of motion. That's always a step number 1, Lagrange, or if you like Lagrange, if not, free body diagrams. So let's do it by free body diagrams, then we get a better sense of that. You can try it later on your own, with Lagrange. So I have two mass. I disturb them by x1 and x2. The free body diagram is simple. So over here, I have, let's say, that force, the reaction, and this guy over there. So this one will be K x1. This one will be K 2K x2 minus x1. And they are the same, action and reaction. And this guy will be K x2. Just pay attention. Oops. When you're writing the equation of motion, just pay attention to the order that we write them. When I write them x2 minus x1, it means that I assume x2 is bigger than x1. So if x2 is bigger than x1, you can visualize. You move it by x2, you move it by x1. So x2 minus x1 is a positive number. That's why I have like a tension load here. The other side is going to be just a reaction. So you could assume x1 is bigger than x2, and then the rest. Just the direction of these forces will be opposite, but at the end, you will get the same result. So obviously, the Newton laws, sum of the forces ma, I would get minus k x1, 2k x2 minus x1 equal to mx double dot. And for the second one, I have k x2, 2k x2 minus x1 equal to mx double dot. Right. So I just organize them. So let's organize them in a, so I would have mx double dot, then I have 3k x1 then that guy is going to be negative minus 2 x2 equal to 0 mx double dot plus 3k x2 minus 2k x1 equal to 0. Let's just make sure that I didn't make any calculation mistake. Mx double dot 2 and 1, 3 gives me that one, and minus 2, seems okay. Yes. Is it 2? Yeah, you're right. This is 2, right? So is it 2? Then that's 2x2. So then the result change, right? So let's correct that one then. 2k x2 thank you. So let's make sure that everything is correct here. K x1, right? This is 2k x2 minus x1. We assume x2 is bigger, so this is tension. So seems okay over here. So that's right, yes. So it will give me then, okay. So it will be mx double dot this one, right? And then we have 3k x1 minus 2k x2 equal to 0. And this one mx double dot, then 3k x2 and minus 2k x1 equal to 0. Is it correct now? Oh, fully? Oh, yeah, they should be numbered. X double dot 1, x double dot 2. 1, 2. Thanks, Francis. Yeah, x double dot also different for these two systems. All right. Eventually, we got it right. These are equations. Now we write them. Step number 2. Write in matrix format. So that's easy. We'll have M0, 0, M x double dot 1, x double dot 2 plus this guy 3k minus 2k and minus 2k, 3k, x1, x2 equal to 0. And let's again stop here, make sure that I'm good. Seems okay. All right, so that's step number 2. All right, no mistake, good. Second one. This is minus 2k, right? This is minus 2k. And they are no, seems like that. Oh, that's fine. Okay, so no, it's always good to check. I rather to write the equations with you here rather than just having them on a slide ready and even making mistakes, sometimes intentionally, so to make sure that you are listening. Okay, so matrix format, we have them in matrix format. Now this is what we are going to call M, the mass matrix, and this is what we're going to call the stiffness matrix. Step number 3, let's check M and K to make sure that they are correct. And we have some rules. Remember last lectures. So let's quickly check them together. Let's take a look at mass matrix. It is diagonal. Right? The reason that I emphasize because soon we need this information. You will see. It is diagonal, right? And physically, if you look at the system, if I remove the stiffness, okay, so you will see these two are independent. There is no connection between them if I remove the stiffness. And we expect the mass matrix to be diagonal. What are the value for diagonal? For each variable, we have the mass. So I have M and N. If the second one was, for example, 2M, I had 2M in that matrix. So it means my M matrix is correct. Look at the stiffness matrix. It's not diagonal because these two systems, they are connected. There is a connection between them, and that connection is that guy. Right? They are connected. So the stiffness matrix is coupled. We say this system, they are coupled with their stiffness. So on diagonal, off diagonal, these members should be the stiffness of that things that connect them with a negative sign. So we have 2K, and this 2K is there with negative sign. So correct. Look at the diagonal. On the diagonal, the stiffness must be sum of the stiffness that attach to each variable. So to x1, I have K, and I have 2K. Some of them is 3K. To x2, I have 2K and K. Some of them is 3K. So check, we are good. Later, maybe, of course, in your exam, you will be asked to develop these equations. But usually I advise first develop the equation and use step 3 as a check. But later, you can just write M and K using step number 3 without writing the equations or bothering about Lagrange or Newton law. Because that rule is always true. So that's a step number 3. Step number 4, find natural frequencies. All right. So to find the natural frequencies, we have the equation, determinant of K minus omega squared M equal to 0. Let's put one extra line next to them so you know when I'm writing K and M, I mean the matrix. So this is not I. Oh no, that's misleading, right? Forget that. It was a bad idea. So capital K and capital M. So rather than just having square root of K over M, now we have an equation. So that's easy to find. This is going to be determinant of 3K minus 2. So K minus that one, M omega squared, 2K, 3K minus M omega squared equal to 0. Right, determinant of that things. Let's stop, make sure the calculation is correct. K minus omega squared M. Yes. So determinant of that thing is equal to 0. I will find omega, one answer K over M, and another one 5K over M. Equations are symmetric, right? You multiply them, so then we decided that, or not us, that was the rule. We put them in order from smallest to largest, and we call the smallest omega 1, the lowest omega 1, the second one omega 2, and so on, if you have more than 2. So, like in this case, we say the lower natural frequency, the higher natural frequency, and so on. So, we found the natural frequency of this system. There are 2. The step number 5, finding the mode shapes or the ratios. Ratios of x1 over x2. To do that, we need to solve k minus omega 2m x1, x2. This is all the stuff that we explained on Friday, right? We start by putting x equal ei omega t, and we ended up with this equation, which we are going to use now. So every time you solve them, you don't need to do the things that we did on Friday. We put x equal to e to the power of I omega t and so on. We'll just use the result. So here is plan. We want to find out the ratio of x1 over x2. This is the equation. Let's write it down. So from that, I'm going to have 3k m omega 2 x1, 2k x2 equal to 0, and 2k x1, 3k minus m omega squared x2 equal to 0, right? Just algebra. I substitute the matrix K, matrix M, and multiply these two matrices. I've got these two equations. So you guys are still with me? This is what happened. If we wrote the equations, and now we want to find the ratio of x1 to x2. If you recall, on Friday, we showed that it doesn't matter which of them you use. You will get the same answer. It's up to you, either with the first one or the second one. We showed it, we proved it, and they are all gives us the same answer. Let's use the first one, but that's your personal choice. So from the first one, all you need to do is, I'm glad here that I have an extra pages. It means I thought about it. So x1, x2 is going to be 2k divided by 3k minus m omega squared, right? So one time, just substitute omega equal to omega 1. You will find x1 over x2. Let's put omega equal to omega 1, which is square root of k over m. 2 gives me 1. And one time, just substitute it by omega 2. And find x1 over x2, 5, 2, minus 1. But somebody please check to make sure these numbers are correct. Okay. All right. So since we are good, now step number 6, summarize everything that we found. Summarize result. So this is what we found. We found we have omega 1 for this system, which is k over m. And we found the first mode shapes, which is 1 and 1. Remember, we decided to show them like that. Rather than the ratio, we show them like that. And omega 2 is 5k over m. Mode shape 2, not x2, x2 is If I put these things 1, it is minus 1. So nothing special so far. Now step number 7. We need to find the motion, right? Find x1t and x2t using the initial conditions. So I need to write down the equation that I had. Let me write it down again here. We had x1t, x2t is equal to a constant mode shape 1 cosine omega 1t plus b still mode shape 1 sine omega 1t. If I had 1 degree of freedom system, that was it. I had only a cosine plus b sine, but we have another natural frequency. So I have c this time x2 cosine omega 2t make some room here. Plus d x2 sine omega 2t. All right. So let's substitute these things. So I have x1t, x2t is equal to a11 cosine omega 1t plus b11 sine omega 1t. Oh, lots of writing. Minus 1 cosine omega 2t minus 1 sine omega 2t. Right? And we have omega 1 and omega 2. So this is the equation that we need to solve. We have 4 unknowns. We have 4 initial conditions. Let's put the initial conditions that we have. I'm going to go 1 slide back and see what is my initial conditions. So my initial conditions says at time 0, x1 is 10, x2 is 0, right? So when t is equals 0, this guy is 10, this guy is 0. Let's put the rest. A 1 plus c minus 1 1. So I need velocity, so I need to take the derivatives. So let's take the derivatives. I need to write down the above equation one more time, but this time x dot t, x dot 2t. Just simply take the derivatives. They are all constant. This is omega 1, and this is minus sine omega 1t. So this guy will be b omega 1 cosine omega 1t. This guy will be c, or better minus c omega 2 minus 1 sine omega 2t. I know it's a little bit boring, but this is what we have to do, all this step. They're just boring, not difficult, right? So I took the derivatives. Let's just make sure cosine sine, sine cosine, sine cosine, and negative over there, and they have that, right? So my initial condition at time t equal to 0, we know the velocity. I'm going to go 1 slide back to check the velocity. And also, please, you make sure that I'm right. My velocity for x1 is 0. My velocity for the second one is 20. So I have then 0, 20. They can be any numbers. But for this example, I just put them there. So I will have B omega 1, 1, 1. And then I have D omega 2, minus 1, 1. Because sine gives me 0. All right. So we have this guy, we have that guy, right? Let's put them together and see if we can find all these unknowns. So I'm going to have A minus C equal to 10, A plus C is equal to 0. And then I have B plus D omega 2 equal to 1. And we have B omega 1. B omega 1 plus D omega 2 or minus D omega 2. So B omega 1, D omega 2 equal to 0. And this guy, I have B omega 1, D omega 2 equal to 20. Are they correct or no? Seems correct, right? So let's solve this one. Of course, from here, I can find out that A has to be equal to 5 and C has to be equal to, is A is 5, C is minus 5. From here, I can find B, which is, you can find B anyway, right? Or it's going to be 20 divided by, or 10 divided by omega 1, and D is going to be equal to 10 divided by omega 2. But please go home later and check the calculations. It's just some algebra. I quickly wrote them and make sure that they are correct. All right. So we found A, B, C, D, and so it means we solved the equations of motion. We found x1 and x2, right? And let's say if in this example, which K was 100 and M was 1 kilogram, my omega 1 will be 10 and my omega 2 will be 10 square root of 5. So I have all these things and I can substitute them. So my the answer then will be, the final answer will be, so x1t, x2t will be all these things that we found. 5, and then 1, 1, cosine 10t, and then we have B, which is becomes 1, 1, 1, sine 10t, and then we have C, which is minus 5, minus 1, 1, cosine omega 2t, and then eventually D, which is going to be 1 over square root of 5 sine 10 5t. So we managed to find x1t and x2t. Each of them is an independent equation, and each of them has sine and cosine in it, and each of them, they have the frequency coming from omega-1 and omega-2. I'll let you to write them separately because the first row is my x1, the second row is my x2. And you can plot them, right? All right. So far we are good, except if there is a numerical mistake, which you're going to correct, go home, correct them. I hope you follow these 7 steps, okay? And they are straightforward. They will be the same for any other question that you will solve. But here is the punchline. We want to do something else with this information. And please forget what happened and focus on this part. So I'll let you to write later. I just want your attention for a minute. Take a look at this system. There is something about this system. First of all, it's symmetric. Do you agree? The thing is same, 2 similar math, k and k in the middle, 2k or whatever. Right? So remember on Friday we said what a system naturally would like to do, and we call it mode shapes. Mode shapes, in other words, they are the natural way that the system likes to move. Okay. So tell me 2 possible ways that this system can move. Right? Do you agree that it is possible that these 2 masses move to the left and right together? Right? And since they are exactly the same, there is no difference between the left one and the right one, then do you agree that if they move to the left and right, they're gonna move the same amount? And the second way that these 2 masses can move is these 2 masses can move left and right the opposite direction, but again, because they are exactly the same, they're gonna have the same amplitude, okay? So this is what we found solving the equation. We said there is a mode 1, which is 1, 1, and there is a mode 2, which is minus 1, 1. The 1, 1 has this meaning for us, that these 2 masses, they're going to move in the same phase. Remember, we said mode shapes tells us the ratio and the phase, okay? So this one means same direction, same amplitude. All right. Now here is what I want you to pay attention. If these 2 masses, okay, I want your visualization. If these 2 masses move the same amount, same direction in a perfect world, what is the deflection of the stiffness in the middle? Right? Try to visualize it and tell me if in a perfect world these 2 masses move the same direction, move back the same amount. What is the deflection of the stiffness in the middle? 0. If the stiffness is 0, what does it mean? It means it doesn't matter if it is there or it's not, right? So let's then say in mode 1, 2k is useless. So I have if it is useless, if it doesn't do anything for me, I just let it go, remove it. What about mode 2? and this is K, right? This is K, this is M, this is K, this is M, and of course they are in mode 2. So now I want you to answer this one. What about mode 2? Mode 2, these two in opposite direction. Again, in a perfect world, we showed that the ratio is 1, right? Or -1, and they are in opposite direction. So mode 2 then, mode 2, opposite direction, same amplitude. Opposite direction, same amplitude. Now tell me, try to visualize it. Now what's the deal with the stiffness in the middle? They go opposite direction. If you watch these things, do you agree with me that the point in the middle, let's say just one point exactly in the middle, that point is not going to move at all on the spring? Do you agree with that? These two, left and right, you set a camera, the point in the middle of that spring is not going to move to the left and right. So it means I can fix it to the ground. I can fix it to the wall, right? There is still, my system will be the same. So if I fix that point to the ground, it means the left, right, and right system, they are going to behave independently. They're not affecting each other. So let's just draw one of them. So this guy is K, right? I cut a spring to half. These two springs, they were parallel. So the stiffness now is 4K. You learned it in lecture 1. Springs, series, and parallel. So it is 4K. So that's my mode 2. And what we say here is, let's call that point A. Point A is a node. Or some people call it a knot, but it's a node. That's a correct terminology. That's a node in our system. A node is a point, no displacement. All right. Sentence. We used the mode shapes and we managed to turn or to convert a 2 degree of freedom system to 2 independent 1 degree of freedom system, right? This is a 1 degree of freedom system. And what is its natural frequency? K over M. This one, what is its natural frequency? 4K, 1K, they are parallel. They are parallel, right? Same displacement. So you can, remember we said parallel for series stiffness. Parallel was when the displacement is the same. So this is 5K now. Okay. So this is 5K equivalent. And we know the natural frequency of this system is, oh, I already did, wrote it there. Is 5K over M. All right. So why we did that? Because single degree of freedom systems or SDOF systems, they are easy to deal with. We are familiar with them. We know what to do with them. All right. Rather than solving all those matrices, we prefer to convert n degree of freedom system to n 1 degree of freedom system. And this is what we did here. Because with the 1 degree of freedom system, we know how to find the natural frequency and done. Yes.
Well, to find the mode shape, you have to do a lot of basic math anyway. So how do you know how to make it into a single dimension?
That's a good question. So if you look at this system, we have a systematic way to do that, but he's right. He's saying to get to that point, to realize that your mode 1, mode 2 are these numbers, you have to do lots of work anyway. But if you just go and look at this system, can you guess what are the mode shapes? Because this is symmetric. You can guess, right? This system, either they are moving one direction in the opposite direction. Let's continue this discussion on Wednesday, but there is a systematic way to find it. Thank you very much for listening.